Hi, so today we're going to talk about 1.5, analyzing graphs of functions. Excuse me. We are going to look at all different kinds of graphs today and talk kind of about some different elements to graphs of how we can identify important pieces of the graphs that might be helpful to us in the future. My pen, just so you know, is out of battery, so I'm going to write with my finger. I apologize. It does not look nearly as pretty. So the first question that we're going to look at is this graph, and it says find all of the places where g of x is equal to x. So really what we're thinking about here is what are all of the places where y is equal to x. Okay, so take a look at this graph for a moment and just see if you can find those locations. All right, the first one that you probably noticed is this one right here. That would be the point 2, 2. That doesn't want to let me make a point. There's also a point down here that would be at negative 2, 2. Sorry, negative 2. And then lastly, the one that tends to not be seen as easily is there's a point right here, which would be the point 1, 1. Okay, so it's important for us to be able to identify what a question is asking, where g of x is equal to x. What does that actually mean? Well, where is x equal to y? The next piece to this is talking about domain and range. The domain is all of the possible numbers that you can put into a function. So again, that would be all of the x values. Okay, the range would be all of the possible numbers that you can get out of a function. So that would be all of the y values. So if I'm asked to find the domain and the range, and I apologize, these graphs are a little bit blurry, but I think we can still see them enough to be able to do this. The domain will be all of the x values, I'll do the domain in red, all of the x values that would span across the graph. So notice this graph would continue going on forever and ever and ever. There's no x value that would not be plugged into this equation. So our domain in this case would be all real numbers. Now, I don't want you guys to write out all real numbers. We've been working a lot with interval notation, so I want you to actually use the interval notation for this. So to write all real numbers in interval notation, you'd be going all the way from negative infinity up to positive infinity. In blue, I'll do the range. So the range would be all of the y values that we're looking at. So here's our y values. Notice that we don't go on forever and ever and ever. So all of the y values that would be hit for our range would be between, this is 1 up here, and negative 1. So we would go from 1 to negative 1. Could I actually equal? Yes, I can. So we want to have brackets. So this would be negative 1 to positive 1. Sorry. Let me erase that. To positive 1. Okay, again, that's a bracket there. So basically, we're just looking, what are all the possible x's? What are all the possible y's? Go ahead and press pause and try the second one. Okay, for the second one, we'd be looking at the domain. Oops. The domain would be all real numbers again. With a parabola, we can go from negative infinity all the way over to positive infinity. It's a really bad infinity, I apologize. And then the range would be, well, the range of values starts here at 1 and then it goes up forever. So I would go from 1 up to positive infinity. Okay, oh, and I can equal 1, can't I? So I have a bracket there. Increasing and decreasing. For increasing, notice that we're always going to go from x1 to x2 and we're going from small up to big. So basically what I'm saying is that if you are increasing, as you move from left to right on your graph, the f of x values or the y values would be going up. Y goes up. Okay, if you're decreasing as you move from left to right for the x values, the y is going to go down. And then for constants, as you move from left to right, y is going to stay the same. So on this graph, I would be increasing here, then I would be constant, and then I would be decreasing. Okay, so what we're going to ask you to do is we're going to ask you to identify on a graph where is the graph increasing, decreasing, or constant. And again, we want to write this in interval notations because we're talking about an interval of numbers. So here's my example. If I have this graph, where am I increasing, decreasing, or constant? So first, let's go ahead and talk about increasing. I would be increasing, I'm going to draw this in kind of in yellow, up to that point. I would also be increasing again from there. I guess it's a little hard to see, so I will write in orange. So I would be increasing from left to right. We always want to go small to big, and we're going to list the x values when we're using our interval notation. So I'd be increasing from negative infinity all the way out here, all the way over to this point. And again, kind of hard to see. This value here is at the point 1. So I'd go from negative infinity all the way over to 1. Then I am increasing again from 1 up to positive infinity. Now, something that tends to be confusing to people is my use of parentheses here. At any given point, if I were to ask you, what is the graph doing at 1? You wouldn't be able to tell me if it's decreasing or increasing or decreasing, okay? You would have to tell me that it's just there, right? You're just at the point. It's not even really constant because there's no movement from left to right. So we're going to always use parentheses because we're not actually increasing at 1 or increasing at -1. I'm noticing I forgot my negative here. I apologize. We're not actually increasing at that point, but up to that point we are increasing. Now the other piece to this, and I'll do this part in green, is where are we decreasing? So we're decreasing from that -1 to 1. So decrease would go from -1, again, not equal to 1. This is increase. Okay? So when you're going ahead and going through those, you'll look at the graph, kind of determine where they are, and make sure that you're only using parentheses. All right, next piece to this is the relative minimum and maximum. So a relative minimum and maximum are basically the minimums and maximums for the graph, but not necessarily the most minimum and maximum. So it's a minimum and maximum of a specific area of the graph. So for example, looking at this relative maximum, notice that my graph actually goes all the way up here to positive infinity. So positive infinity would really truly be the maximum of this graph. However, with the relative maximum, I'm looking basically at, in this particular region here, where is the maximum value in that region. So a graph, it's possible for a graph to have multiple relative minimums, multiple relative maximums. That's why they're relative. They're relative to the area that they are in, okay? So by definition, a relative maximum, f of a, is a relative max if x1 is less than x is less than x2, so that means that as we're moving from left to right, the f of a is greater than f of x. So essentially what we're saying is that the a value, or that x value that we would plug in, the output from that is greater than any other output that you would get from that particular location, okay? Relative minimum at the same time, as we're moving left to right on our graph, if the output of your minimum is less than the output of any of the other minimums in that general region, then it would be a relative minimum. Even and odd functions. Even and odd is another way to test symmetry. Okay, Back when we were testing symmetry before, we talked about x-axis symmetry, we talked about y-axis symmetry, and we talked about origin symmetry. Here's the deal with x-axis symmetry. Our x-axis symmetry looks something like this. The problem is that that is no longer a function, right? Or it's not a function because it doesn't pass a vertical line test. So it's not possible to have x-axis symmetry with a function. So we don't even need to really worry about that. With the y-axis symmetry, we looked something like this. That was really not symmetric across the y-axis, but you get the idea. And then for origin symmetry, we looked something like this, okay? So those both are possibilities for functions because notice both of these graphs would pass that vertical line test, okay? So a function is even when f of negative x is equal to f of x. Even is when we have y-axis symmetry. Okay? Because notice I'm plugging in negative x and I'm getting out positive y. This is the same as what we talked about earlier in this chapter. If we plug in negative x and we get out a positive y, then we would have we would have even symmetry. I want to jump down before I do this example and jump down to where there's odd. So if a function is odd, that would have origin symmetry. And notice that I'm still plugging in negative x, and this time I'm getting out a negative y. So negative x, negative y. That's why it's the same as origin symmetry, okay? Now, when we plug these in, essentially what we can do is, notice for both of these, we're going to take the same first step. We're going to have plug in negative x. So that's always your first step. I'll write that over here. Step 1, plug in negative x. Okay, so for this first one, if I have f of negative x, that would be equal to negative x squared minus 4. So that would be x squared minus 4. Notice that what I get out from this is the exact same as what my original function was. That's what I want. I want my function to be the exact same. One way that I like to remember this is I like to remember if when you plug in negative x, if what you get out is the exact same, then it's even. Okay? Check out what happens with with the odd one. So if I do f of negative x, I get negative x cubed plus 2 times negative x. So this would be negative x cubed is the same thing as negative x cubed minus 2x. Notice that these two things are the exact opposite, which is what I want for an odd function, right? I want the negative version of f of x. So if we have the exact opposite, then our function is odd, okay? So even, odd, if it's exact same when we plug in negative x, then we have an even function. If it's the exact opposite, then it's odd. All right, the last topic for today is dealing with zeros. The x values for which, the zeros are the x values for which f of x is 0. So this is basically asking us, when is y equal to 0? Or in other terms, when is y equal to 0? Well, that happens here along the x-axis. So really we're finding the x-intercepts, okay? But when we talk about zeros, when you were back in your algebra class, your x-intercepts we always wrote as a number, comma, 0, right? With zeros, you actually don't need to do that. You can just list what the value is because we're talking about the 0, not the actual point. So for each function, we're going to be asked to find the zeros. So basically all that we're going to do is we're going to plug in 0 for f of x and then use different methods that you have to solve. So if you have 2x squared plus 13x minus 24, you might need to factor that one. So maybe it's 2x and x. And if you couldn't figure out how to factor this, we could also use the quadratic formula or completing the square, whatever works best for you. So I would do, let's see, what could we try? Maybe 8 and 3. I have 8 and 3. I would have This would be 16. Ooh, I chose right. This would be 16. This would be 13, or sorry, 3x. And if I do 16 minus 3x, that would give us our 13x that's in our center. If you had a different method for factoring, that's just fine. So then I would go ahead and say, all right, well, now let's set each of those pieces equal to 0. 2x minus 3 is equal to 0. X plus 8 is equal to 0. So x would equal, if I add 3 and then divide by 2, I'd have 3 halves, or x would equal negative 8. Okay, so the zeros are 3 halves and negative 8. Go ahead and press pause one more time. Give this second one a try. It's a little bit of a different question, and then when you're ready, press play and I will do the answer. Okay, for g of t, we're going to do the same thing. We're going to set g of t equal to 0, and we have the square root of t minus 25. And in this case, we just want to square both sides, which ends up being t minus 25 is equal to 0. So 0, oh, sorry, not 0. So t would have to equal 25, which makes sense, right? If t was 25, that's the only thing that would make this equal to 0. Later this chapter, we're going to talk about the graph of this, and the graph of this would look something like this. Okay, so notice that there's only one x-intercept there. Okay. All right, so those are all of the topics. I know I didn't go over a lot of examples because I wanted to give you some time to actually work on your homework. So your job for the rest of the class period is to work through your homework assignment. If you have any questions, feel free to ask your neighbors or ask me if I'm in your class. Otherwise, I will be available to answer any questions that you guys have on Monday as well. So have a great weekend, and I will see you later.